Exercise 6J, General Solutions. Today we are going to learn about general solutions of circular functions, and what you need to be able to do is understand the rule for each of sine, cos, and tan general solutions, and hence be able to find those general solutions given an equation. So just so that we could understand what on earth we're talking about today, what I want you to do is to grab your CAS calculator and solve this equation over the domain of 0 to 2 pi. So I'm going to switch in a moment to the CAS calculator. If you haven't typed it in yet, please pause the video and give it a shot yourself. So this is what it should look like. Solve tan 3x is equal to root 3, and our domain is between 0 to 2 pi. If you're unsure how to get that straight line there, which determines the domain, it is control and equals, but it's the equals that indicates or provides for you the options for inequality. So it's at the top left-hand corner. So once we press enter and make sure your calculator is in radians, what you'll notice is that you will get multiple solutions there. And that is for actually it'll be for 6 cycles of tan because tan goes for 1 pi. So we have 6 intercepts there, and it's for 6 cycles of tan. The thing is though, what happens if I ask you to do this but for no domain? So once again, I'll get you to type into the equation, but no domain this time. And if we press enter, what we'll see is we'll get this really weird looking equation. And I know that all of you have seen this before, and it's always because you forget to write in a domain. So that's what we're learning about today. What does this mean? The idea here is that we don't have a domain. We are solving for every possible value of x from negative infinity to infinity. So of course, circular functions, your sine, cos, and tan, they're periodic functions. They are going to repeat over and over again. So of course, there's going to be multiple possible solutions. So what we are looking for is a rule that defines any one of those solutions, and all the n is it just asks us which cycle are we looking for. Are we talking about the first cycle, the third cycle, the 50th cycle, whatever it is, we can substitute into n and we will get our answer. So that's what we're doing today. So we do have a specific rule for each of them, but as always, I never want to just tell you this is the rule. I want you to try to understand where it comes from. If it is a little bit confusing, don't stress too much. You don't need to know the background, but I will try to explain it so that you can try to understand where it is coming from. So the first thing I want to just explain is this sine inverse of a. Where does this come from? So if sine x is equal to a, then when I'm solving for x, what I do is I take sine inverse of a. And if you remember, that's when we find our base angle and then we think about which quadrant it's in and so on. Because the idea is that there isn't going to just be one answer. This will only provide me one answer, but I know that there's going to be multiple answers because I will keep going around and around my unit circle, which will provide me with more solutions. So each of these equations here, all they do is tell me what each of those solutions are going to be. But I just wanted to point out that this x is equal to sine inverse of a, and that's where we usually say our base angle is equal to that. So when you see sine inverse of a, what that's really indicating is that that's just your base angle. That's theta. So let's think about sine for a moment. Sine is positive in these two quadrants. Now, it doesn't matter if we're working with the positives or the negatives. The idea is that it's the same in quadrants 1 and 2. Let's think about the rule. So for quadrant 1, it's just theta, and in quadrant 2, it's pi minus theta, because here is pi, and then this is theta, so we're going backwards by theta. So this is theta. If this is also theta, well, I'm starting at pi, then minus that theta. So let's see if I can relate that to these rules that I have at the moment. Let's start with the first one. So this is saying that it's sine inverse of a, so the angle, plus 2n pi. So what is that n? N just tells me how many cycles I have. So if I start here, plus 2n pi is just saying if I want n to be 1, that means I'm going to go around once, and I'll end up in the exact same situation. If I want to go around 10 times, well, I'm going to end up in that same position. So the angle will look a little bit different because I've added 10 pi to it or 20 pi to it, but the idea is it is the same angle, but it's just in a different cycle. So 2n pi just keeps telling me to add 2 pi n number of times, so that's the cycle. So let's try and decipher the second one, which looks a bit more confusing, but really isn't. Let's try and expand it. So we've got our 2n pi again, and then plus pi minus, and remember this is just theta. So pi minus theta gives me my initial angle here. Remember pi minus theta is over here. And then we've got the same situation, plus 2n pi. So this is to get to my next cycle, and then again and again, and however many ends that you want. So that is what these rules read. So they are just our basic rules, theta and pi minus theta, and then all we're doing is we're adding 2 pi to it, however many times that you want. So that's for sine. Cos is very similar. So let's again consider where the angles are the same. Let's just, for this exercise, think about the positives. That's over there. This is theta, and then of course, if this is theta as well, well then this angle would be 2 pi minus theta, because there's 2 pi, and then we minus theta to there. So hopefully at this point you can already start to see the equation. This actually is 2 equations. One of them is the positives. So I start at my angle. Here's theta, and then I'm going to add 2 pi to get there again, however many times that I want. Or what I can do is start at my angle. Well, I wouldn't start at my angle, but I'd start at 2n pi, and then I would minus the angle. So I start here, and then I would subtract the angles however many times. Or you can always think of this particular angle, and then I'm just adding 2n pi to it. I think I went the wrong way around there. No, it's fine. Okay, so we are adding 2n pi to each of them, and it's just using this rule, 2 pi minus theta. So that's that, 2 pi minus theta. And then this is 2 pi plus theta, which is exactly what we're having there. All right, last one. We are going to now do tan. Tan should be the easiest, because where is our angle of positives there? This is theta. This is, of course, pi plus theta. And then, as you can notice, to get there, all I have to do is just add another pi, and then add another pi, and add as many pi's as you like. So the difference between each of these is pi, which is why it's just n pi plus tan inverse theta, or plus the angle. So that one's a really nice one. There's only one equation for tan. So that in a nutshell is where we get each of these equations from. You don't have to, as I said, you don't have to know exactly the background behind them, but I think it just really helps to be able to memorize each of these. So now that we know this, let's go ahead and apply it to a question. Example 15, find the first 3 positive solutions to each of the following equations. Now we can do this through our techniques already of solutions, but today we are going to use general solutions to get to the first 3 positive solutions. So let's begin with our rule. So we're using tan, so we know that if we look at the rule back here, so we've got x equals n pi minus tan inverse of a. So x equals n pi minus tan, plus tan inverse of a. Now I just want to point out one thing. This x is the angle. So whatever the angle is here, it should be here as well. So just be careful with that. It's not just 1x. In this case, it is 3x. What is a in this case? Well, a is root 3, because that's what's on the other side. If I wanted to take the tan over, it would be 3x equals tan inverse of root 3. So I will replace that a with root 3, and now I need to use my exact values to keep this, or to figure this out. So tan inverse of root 3 is going to be pi on 3. And finally, to get x by itself, I'm going to divide everything by 3, and I can make this look just a little bit nicer by making the denominators the same. So I can multiply both of these by 3. That'll be 3n pi plus pi on 9. And I can even go one more step, which is to factorize that pi out. So that'll be 3n plus 1 on 9. Now, any one of these answers from this point onwards is correct. That's totally fine, but it's really nice to just write it on this particular line. And if you notice, so have a look at that, pi bracket 3n plus 1 on 9. Let's go back to our CAS calculator. Have a look at how it's exactly the same. So it's 3n plus 1 pi on 9. So that's just a bit of an interpretation in terms of how we get our general solutions. Now, of course, that's not it. What we want to do is find our first 3 positive solutions. So we're going to now start plugging in numbers for n. The first one we're always going to start with is 0, because that's our first cycle. So in this case, when n is 0, we will have this solution. So that'll be 3 times 0, which is 0, plus 1. So that will just equal 2 pi on 9. And it makes sense that that would be our first solution. Then we will move on to n is equal to 1. So in this case, it's 3 plus 1, which is 4 pi on 9. And then lastly, n is equal to 2 this time it'll be 6 plus 1, which is 7 pi on 9. And if I just wanted to compare it one more time, so we have a look at our answers, pi on 9, 4 pi on 9, 7 pi on 9. If I go back to my CAS calculator, you can see that in my first line, I've got pi on 9, 4 pi on 9, 7 pi on 9. And if I were to continue, I would get the rest of those solutions there as well. Okay, next example, 15. Find the first three positive solutions to each of the following equations. Now for sine, this is going to be a little bit different because remember, sine has two equations. The first equation is for this quadrant, and then the second equation is for this quadrant. So if I'm looking for the first three positive solutions, what looks like is going to happen is I'm going to have first one here, then I need to go around to this angle, so that'll be the second one there, and then I'll be coming back round for the third one here. So you need to make sure you keep in mind that you know which equation you're using your n values for. So let's go ahead and plug in our values. We can go back to look at the formulas if you'd like. So we've got x is equal to 2n pi to 2n pi plus sine inverse of a. So that's, remember, for my first quadrant. I might just write a 1 so I remember that for the first quadrant. You could even write maybe as well the 3 so you know it's for the first and third solution. And then the second one was x is equal to, and that was, I'll just confirm, 2n plus 1 pi, and then minus sine inverse of alpha. And that was because it's in the second quadrant there. And so this is for the second. Now, just as we spoke about before in terms of our angles, remember, whatever is here needs to go over here. So unfortunately, you can't move them around. Sorry about that. If you need to rub out, go ahead and do so. But I'm going to move my x's out a little bit so I can get that in. So whatever the angle is needs to go in the front, and we'll solve for it. Now, what is a? A is our value on this side. So in this case, it's 1 on root 2. And from there, we can go ahead and start plugging in our values. Now, of course, what is sine inverse of 1 on root 2? If you think back to your exact values, it is pi on 4. What I might do in this case, I might just quickly expand the bracket here, just because in a moment we're going to need that. All right, so next step is I'm going to get x by itself, so I'm going to add pi on 6 on both sides. And we're going to try and simplify as well. So that'll be 2n pi, and then we've got pi on 4 plus another pi on 6. The common denominator here would be 12, so I would multiply the 4 by 3. So this would be, I'll just do it in a different color. This would be 3 pi on 12, and then this would be 2 pi on 12. So 3 plus 2 is 5, and then that's on 12. And then for this one, for the second one, we will have 2n pi. Now we've got plus pi minus pi on 4 plus pi on 6. So again, we're just going to quickly change the denominator so it's nice and convenient. So that's 2 pi on 12. And then here I can write this on 12 as well. So that'll be 12 minus 3, which is 9, plus 2, which will be 11. So that'll be plus 11 pi on 12. Now we can put this all on one denominator as well, if that will make that any easier. We've got a large number, so it's not necessary for now, but I'll do it just to show you what it looks like. So to put this over the same denominator, the 2n pi, I would need to multiply that. So it's on 12, so this would be 24. So I'll get 24 plus 5. Oh, sorry, so I won't be able to do that. So it'll be 24n pi plus 5 pi. So what I can do is go 24n plus 5, and then there's a pi on the outside, and that'll be 12. And then for the second solution, same idea, that will be 24. So it'll be 24n plus 11 pi on 12. All right, so now that we have our two equations, what we can do is we can go ahead and start solving them from here. The main reason that we try to put it over one denominator is just because it'll make it a lot easier when you're trying to calculate your final answers. I have run out of space, so I'm just going to pull out another page and copy these equations over. Feel free to start plugging in your n values while I do this. Okay, so as we spoke about, our first and third solution is going to come from this one. It's in the first quadrant, and our second solution is going to come from this one here. So we're going to begin. We always begin with n is equal to 0. In this case, x will equal 24 times 0 plus 5 pi on 12. That will be just 5 pi on 12. That's our first solution. Now for our second solution, we're still using n as 0, but we're using it in the second quadrant this time. So x is equal to 24 times 0 plus 11 pi on 12. So that will just be 11 pi on 12. And then for our third solution, we're now moving up to the next number. So n is equal to 1 in our first quadrant. X is equal to 24 times 1 plus 5 pi on 12. So that'll be 24 plus 5, which is 29 pi on 12. And so you would continue in this fashion. Unlike 10 we just used n is 0, 1, 2 because there was only one equation. But this time, because there's two equations, you need to make sure that you use it for each equation to be able to find your solution. So these three here are our first three positive solutions. Last one, which is also 10. It's going to be very similar to what we've done before. Feel free to pause the video at this point and give this a shot by yourself. So I'm going to start straight away by writing the angle in, and that'll be n pi plus tan inverse, and this time 1 on root 3, which is our a value. So again, going a little bit faster this time. So tan inverse of 1 on root 3 is going to be pi on 6, and then plus pi on 3. I'm taking this to the other side right away. I'm now going to put this all on the same denominator, again, right away. So if I want this to be on 6, there will be a 6 there. And this one to be a 6, that becomes 2. So it'll be 6n pi plus 2 pi. Pi plus 2 pi is 3 pi, and then there's 6n there. So I can do 6n plus 3 pi on 6. So all I've done is I have just gone a little bit faster with this one. You can notice, hopefully, that you can actually pull out a factor of 3 at the top there, and we can simplify that with the bottom as well. So if I pull out a factor of 3, from the top, that would be 3, 2n plus 1 pi on 6. That can simplify to 2. So my final equation would be 2n plus 1 pi on 2. And now, because of tan having only one equation, I'll go through my n's. So n is equal to 0, 2 times 0 plus 1 pi on 2. That'll be pi on 2. Next, that'll be 2 plus 1, which is 3. And finally, our last one. So 2 times 2 is 4 plus 2. Sorry, that should be a 1. 4 plus 1 will be 5. So that'll be 5 pi on 2. So as you can notice, once you get the hang of it, it's actually quite a quick process. And you can choose to use this instead of solving equations the normal way. I think that this is quite an efficient method if you feel like you understand general solutions to being able to find all the solutions that you can possibly need. So that's it. That's exercise 6J for general solutions.